Hello everybody, welcome to the Gather Knowledge with Mihai channel. This video is part of the series covering useful C++ features from different standards. In this video, we will be talking about 6 useful C++ features from C++20. There will be many more on the C++20 series as well as on the other standards, some of them being already underway. Without further ado, let's get started. Small disclaimer, among this list I am excluding the biggest known features such as concepts or coroutines or modules. I'll make a video about each one of them independently. First up on the list is the spaceship operator. This is a feature that I was really waiting for and that I kept on using since C++20 was released. The spaceship operator is a new operator introduced in C++20 that offers an easier alternative to provide the class with all comparison operators at once instead of writing 6 functions. The function signature would look something like this. We have a class object and inside of it we declare the operator function. The operator denoted by the symbol smaller than, equal, greater than can be used to compare two objects of the same type. It returns one of the three possible values, -1 if the left operand is less than the right operand, 0 if they are equal, and 1 if the left operand is greater than the right operand. This operator greatly simplifies the implementation of comparison function and is particularly useful for sorting and searching algorithms. So we would use the spaceship operator to generate automatically all the comparison operators to reduce the boilerplate code. So now instead of writing multiple comparison operators, you just write one single function. Let's go for a real world example where we would use something like this. Let's say we have a class version that has 3 members as integers, a major, a minor, and a patch version. Now we only have to implement the spaceship operator for this class to automatically generate all comparison functions that we need. By defining this operator function, we are now able to use all comparison operators that we need. As such, we can start to directly compare versions between them. Now, let's say we have two versions, v1 which is 5.3.12 and then v2 which is 5.6.44. We can write immediately the code to compare these versions to see which one is less or earlier, greater, or if the versions are equal. Let's also run this program and see the output. Version 1 is less or earlier than version 2. That is correct. So this is a scenario which proves the usefulness of the spaceship operator in a real-life use case. The second feature that I would like to talk about in this video is stdspan. Stdspan is a known owning when known owning is the keyword here, view over a continuous sequence of elements, such as arrays, stdvector, or other memory contiguous container-like types. It allows functions to accept ranges of elements without needing to know the specific container type. It provides a safe and flexible way to access and manipulate these sequences without copying data or allocated memory. So, what are the key characteristics? It is known owning, as I mentioned earlier, doesn't manage memory. It only provides a view into an existing block of memory. It's bound safe, so unlike core pointers, stdspan knows its size, making it safer and less error prone, and it's templatized. You can use it with any data type, such as integer, float, or other custom types, and any contiguous memory storage, such as arrays and stdvector. Let's look over 3 examples where stdspan would be really useful in real life. First one would be the interoperability with C APIs, which in my opinion is the most useful example for stdspan. So let's say you have a function written in a C style. Let's say I have a function which is called printArray, which takes in an array pointer and a size, iterates through the size of the array and prints out every element of the array. Now let's consider we have an array of 5 elements. I want now to be able to call this function in a flexible and safe way. This is why I create a stdspan object, which provides a view into the array. So the program works and the output is correct. I just printed every value in the array using the printArray function. For an array, stdspan doesn't offer, in this case, a lot of advantages, as the array are already C style. However, when we deal with a stdvector, stdspan shows its usefulness. Let's consider we have a stdvector this time, and we want to call the printArray function. We simply create a span from this stdvector, and then we call the printArray function using the stdspan. And now let's verify that this works. Excellent, we managed to call a function written in C by providing a StudSpan object, which acts as a view into the stud vector. We no longer have to worry about introducing the correct pointer or size. StudSpan handles that for us, making it less error prone. However, as mentioned earlier, keep in mind that StudSpan works for containers with contiguous memory such as arrays and vectors. It doesn't work for types such as lists. A second useful example for StudSpan is how easy it is to create a partial view of the contiguous memory using the subspan function to obtain another partial StudSpan object. So for example, if I use this example here, but I don't want to iterate the whole array, I just want to iterate through a subsection, I can simply create another span and iterate through that. The subspan function takes the index of the first element and the index of the last element from which to create the subspan. As such, when we iterate through the subspan, we print 2, 3, 4 because we took the subspan from index 1 to index 3, which is exactly 2, 3, 4. Let's go to the third most useful feature of C++20, templated lambdas. C++20 introduced templated lambdas with explicit template parameters, allowing developers to specify template parameters directly within a lambda expression. This makes generic programming more expressive and flexible, while it improves readability. Before C++20, lambdas could be templated only by relying on auto parameters like this. However, you couldn't explicitly specify template parameters like you would in a normal function template. In C++20, you can write something similar to a normal templated function. Now let's go to some use cases of the templated lambdas. A first use case would be that you can easily pass more things to one lambda, even if you don't use SFINAE, which is an acronym which stands for substitution failure is not an error, which is used to deduce parameter types in templated programming. Now I can call this function using a vector or using an initializer list, for example. How can we differentiate the two calls? Suppose we want this function to only accept a stud vector because we need a contiguous memory container, like we need it for StudSpan. We can try a static assert. However, there is no simple way of doing this and it needs to be implemented using concepts or advanced templated logic using SFINAE. So the check in this function to see if we are indeed dealing with a vector is quite complicated to be done in lambdas of older C++ versions. Using the new templated lambdas, this can be easily done. We just have to templatize this function and pass in a stud vector. Now, we are no longer allowed to pass in the stud initializer list because the templated lambda accepts only a templated stud vector. The error thrown is the standard error saying that it cannot find a match to the function we are trying to call, because the arguments don't match. We are trying to pass in a stud initializer list where a stud vector is expected. Let's comment out the function call using stud initializer list, recompile and run the program. As you can see, the program compiles and the function is called only for stud vector. We stumble on a second use case when a templated lambda function has multiple arguments and we want them to have the same type. That was previously more verbose than it is right now. There are these print container functions, where the first one is the generalized templatized version and the other ones are specializations for stud vector of integer and stud vector of double. Let's also write a lambda function that takes two arguments. So I want to have two vectors, one of type integer and one of type double. And now let's call this function and see what happens. Calling the function doesn't pose any problems, as auto for vec1 deduces to a stud vector of integer and auto for vec2 deduces to a stud vector of double, and the respective print container functions are called further down the line. But this is exactly the problem. We might not want different specializations to be triggered, we might want these types to be exactly the same, and it has happened to me that I really needed this. As I said earlier, this is also possible to be done in older C++ versions, but it is more verbose. In order to do this, we use decal type specifier. So now, when we try to compile, we will get an error because the argument types passed to our lambda function are expected to be the same. If we modify the second argument to also be of type vector of integer, then it will compile and work. But this is now easier to be done in C++20 with templated lambdas. Now I can be sure that they both have the same type, so now it works. Now this function compiles, but if I type here the second vector, this won't compile again. This right now throws an error stating again the standard error that one gets when working with templates, that there was no match found for our call. Let's move on to the last use of the templated lambdas. However, I haven't encountered this so often, but the templated lambdas also prove to simplify the syntax in this case, as previously one had to use once again decal type to obtain the type for a perfect forwarding inside the lambda. So in this case I have two functions, one takes an R value reference and another one takes an L value reference. Now let's consider we have a templated lambda function, in the first case with auto, that calls this function using perfect forwarding to match the type of the function argument, an R value or an L value in this case. So now if I want to do the perfect formatting, I have to use decal type. Let's try it out by declaring some variables. I created two variables, some num and another num. Yes, I didn't have much inspiration about that, sorry. Some num is an integer representing the value 121 and another num is a reference to some num. The first two calls of the lambda functions on lines 22 and 23 will call the L value reference overload, while the calls on the lines 24 and 25 will trigger the L value reference overload of my function. Let's see if it's exactly the case. So yes, so for the first two we call the L value reference and for the second two we call the R value reference. But we can do this more easily now using templated lambdas. Now I don't need to use auto anymore, I just have to declare the type name t and I simply specify the stood forward of t. And let's check if this works. Perfect. Now we call the L value for the first two, L value reference of the overload for the first two, and then we call the R value reference of the overload for the second two. The fourth feature that I want to go through in this video is the formatting library. C++20 introduced a new std format library that provides type-safe and efficient string formatting. It is based on the widely used Python type formatting, offering a much more powerful and intuitive alternative to the traditional std_cout and printf methods. This feature helps developers format text, numbers, and variables into strings with a much simpler and cleaner syntax without the risk of format string vulnerabilities. The core of this feature is the std_format function, which formats strings using replacement fields, the curly brackets, that are replaced with the provided arguments. Too much talking. Let's go for an example. I just created two variables, a name as string and an age as integer. Using std_format, I create a new string that I pass to stdout. As you can see, std_format can take any number of arguments, replacing the curly brackets provided in the first string with the respective argument. In this case, I have provided two brackets and two arguments, name and age. Let's run this. So now everything is printed correctly. One can also format numbers with different options like padding, alignment, and decimal precision. Let's go into an example. Here I declared the double pi that we all know, the 3, 14, 15, 9. And the .2f format specifier indicates that pi should be printed with 2 decimal places. When I run the program now, I say get pi as 314, which is exactly 2 decimals. And also we can format hexadecimal, octal, and binary. The decimal is the default specifier. But I can also specify hexadecimal, or octal, or binary. Let's run this and see the output. So I get 42 as decimal, the hexadecimal representation is 2a, the octal is 52, and the binary would be 101010. What I presented here is just a small intro of std_format, but it is capable of a lot more. This is again a feature that I use in almost any project, since it was introduced in C++20. The next feature I wanted to talk about is the calendar and time zone library. The kernel library of C++11.14 was extended with a calendar and time zone feature. C++20 introduces a comprehensive library for handling dates and times, which includes time zones. This library is based on the popular datetime library by Howard Hinand and provides a much needed standard way to work with time-related data. Let's start with the basic, working with dates. One of the new types added in C++20 is the std chrono year, month, day, which represents, you guessed it, a year, a month, and a day. It's straightforward and a much needed improvement. First of all, I'm going to declare the namespace to use with it, the std chrono and std literals. This is how I declare the date for the 1st of January 2025. And now I can simply output it. When I run this, I get exactly the date that I have just declared, the 1st of January 2025. Another good use case for the calendar and time zone library is getting the time in different time zones. So let's go through an example. Here, we are getting the current time in UTC using system clock now static function, and we convert it to New York time zone using zoned time. The zoned time constructor takes two arguments, the name of the time zone and the time you want to convert to. On second thought, let's also print the UTC time as well. For that, I'm going to use the stud ferment library that we have just discussed. Let's see the output of the program. Basically, right now, as you can see, in New York it's 2:30 in the afternoon, and on the UTC time zone, such as in London, it's 7:30 in the evening. As such, thanks to the calendar and time zone library, we can easily work with time in any time zone. Want to have the daylight saving time? No problem. Zone timed object will automatically adjust based on time zone's rules. This is another great thing about C++20 calendar library, is it comes with built-in support for the IANA time zone database, which is kept up to date with real-world changes. This means that the library understands the complexities of daylight savings and historical time zone changes for you. The last feature that I want to talk about is stud source location. C++20 introduces the stud source location utility, which provides a standardized way to capture information about the current location in source code, such as the file name, function name, line number, and column number. This can be especially useful for logging, debugging, and error handling without manually specifying this information. Previously, developers had to use macros like __file and __line to capture similar information, but stud source location offers a cleaner and more flexible solution. So among the benefits would be the ease of use. It automatically captures the file name, function name, line, and column without requiring manual input from other macros. It improves logging and debugging by providing the necessary context, and it stays safe. Unlike macros, stud source location is a proper class that provides methods to access each part of the location, improving code safety and maintainability. I used it in my projects mostly for logging, and this is exactly the example I'm going to put forward today. This would be my logging function. It takes as arguments a message as string view and the current source location as default argument. I then log the message together with the place in the source code using the previously discussed stud format library. Let's consider afterwards that we have a function that takes in as argument a templated variable x, and we want to do some logging in this function. I also want to log a message in main right before the call to my previously defined function. It's important to notice the lines, so this one is line 20 and this here is line 14. Let's run the code to see how the logging behaves. And as you can see, it prints in both cases the file name, line number, function name, and the message that I attached. In case of templated functions, it outputs, of course, the specialized function, such as in the case of my templatized function, where it is printed as a void func of integer. So this is stud source location. It helped me a great deal with logging since it was introduced, and I almost always use it in my projects. Thank you for watching to the end, and I hope you learned some new things about C++20. I know the video is around 19 minutes, but I wanted to go over a lot of details. Please let me know in the comments what other interesting features of C++ I should go through, what you liked in this video, or how it can be improved. If you liked what you saw, don't forget to like and subscribe, as I'll try to post videos about interesting topics as often as possible. Thank you very much, and see you in the next video.